if you can roll that tape.
Hello, I'm Professor David Newman, the Apollo Program Professor of Astronautics at MIT. It's my great pleasure to introduce you to the Earth Intelligence Engine. This is an amazing team that's come up with novel uses of artificial intelligence, using physics-informed neural nets and GANs, generative adversarial networks, all that to paint the pictures to create the satellite imagery of the future. What will the satellite images look like of the future, especially for Earth systems and coastal flooding? Can we paint that picture in order to benefit humanity, get people out of harm's way, look at the rescue, and just understand all of Earth systems? So important for MIT Portugal to sponsor this project with NASA, because we really are very excited about the work that the team's doing to further climate response and understanding Earth systems better by using artificial intelligence. Why is it important to the world? This work is so important for everyone to have a better understanding, kind of put it in your pocket, have ease of access to satellite imagery of the future, especially for natural disasters, and in this case, extreme coastal flooding, the oceans and the land and where our urban populations are, and to show those satellite images using the artificial intelligence and the tools that the Earth Intelligence Engine team has developed. So glad to introduce them to you.
According to the UN, flooding is the most expensive disaster in the world. Today, floods cost the US billions of dollars every year, and climate change will only increase the frequency and the intensity of these flooding events. Now, imagine a city planner attempting to convince the city council to fund more climate-resilient infrastructure development, perhaps the establishment of seawalls or mangrove protections. So the question then stands, how can this city planner communicate the flood impact most effectively in order to receive the support and the funding for climate-resilient infrastructure development? Today's flood visualizations are either informative, like pixels on a map, or intuitive, like street-level flooding. And what we gathered from our expert interviews was that the color-coded images can be hard to grasp for non-technical decision makers, and our street-level imagery just doesn't have enough information for decision support. So there is a research gap here. And 8 weeks ago, we set out to fill that research gap. Hi, my name is Oceane Boulet, and I'm a researcher on the Earth Intelligence team. I'm from Florida, a place where hurricanes and flooding come in annual seasons. And I'll never forget the moment when I was 10 years old, huddling with my mom in our bathtub as we waited for a massive Hurricane Charlie to blow over Orlando. That moment made me realize how humbling natural forces can be. That is why I am grateful to have been able to be a part of the Earth Intelligence team, where over the past 8 weeks, we have deployed a tool to ease communication between experts and decision makers when it comes to realizing flood impact. We have leveraged generative vision models to create physics-constrained local visualizations of future flooding on the US East Coast. We do this to assist in climate-resilient city planning. In other words, we can now generate satellite imagery of floods that have yet to happen. Throughout this presentation, I will share with you some of the previous research that we've built upon, how we created the physically constrained satellite imagery, and then how we evaluate that imagery. But first, a little bit of the research work that we have built upon. SLOSH is a physics-based storm surge model from NOAA. In general, the SLOSH model output is not very high resolution, but because many government agencies use SLOSH and we want our work to be accessible by those government agencies, we decided that it was very important for us to use SLOSH as well. What we also need, satellite imagery. And we are glad to have had sources for high-resolution satellite imagery, which consisted of pre- and post-flood images of 6 disasters throughout the US. Finally, we need a way to combine the SLOSH model outputs with the satellite imagery. And for that, we turn to a new generative vision technique called a GAN, a Generative Adversarial Network. So we begin with a pre-flood image, like the one you see here. We used an unmodified GAN called Pix2Pix HD to add flooding to these images. And we got an image like this one. The problem is this unmodified GAN, one without a physics-based output, so slosh, for instance, is just adds flooding in randomly because there are no physical constraints. This generated image is off base, and we see this because the ground truth actually says that our post-flood does not have water where the GAN says we should. In other words, we clearly need to modify this GAN. We need physical constraints. So that brings us to the work that we have done. We have created the first physically constrained photorealistic visualizations of coastal floods. This is a satellite image before Hurricane Harvey hit somewhere in Texas. And this is the same location, but now post-flood. Now I'm about to show you a third image. And if we are successful, then the image I'm about to show you will look strikingly similar to the post-flood image you see. Ta-da! As you can see, they're very similar. So now let's dive into how we got this generated image. Our GAN learned the relationship between a pre-flood image, a segmentation map, and a post-flood image. See, during training, the GAN had access to all three of these images, but during inference, we only showed it the pre-flood image and the segmentation map, and we asked it to generate a post-flood image, which it did. We actually ran a few experiments. Just as a reminder, our pre-flood imagery was used as input, and our post-flood imagery, this is what we want our generated imagery to look like. This is the goal. Our initial segmentation map was used as input, and we used it in order to create baseline. So our baseline is essentially takes the pre-flood image and paints all the pixels that are supposed to be water brown. And our GAN looks pretty decent here. We'll go into how we evaluate decent in just a moment. However, in order to visualize future floods, we cannot use high resolution segmentation maps. Why? Well, because these high resolution segmentation maps only exist for past floods. Instead, we hope to leverage slosh, which projects future floods. But remember, the slosh model outputs are usually low resolution, as you see here. Therefore, our baseline also looks pretty pixelated, pretty low resolution. However, our GAN still does reasonably well. And once again, we will go into how we evaluated these imagery in just a moment. But before that, I would like to discuss the metric that we used in order to evaluate these images. Today, there is not, to our knowledge, a metric that measures the trade-off between photorealism and flood physical consistency. That's why we propose the Flood Visualization Plausibility Score, or FVIPS. LPIPS is a perceptual similarity metric that helps us compare these two images, whereas the intersection over union, or IOU, is a metric for how well our predicted segmentation lines up with the actual segmentations from the NOAA storm surge models. By combining LPIPS and IOU, we can now assess photorealism and physical consistency. So now that we've discussed how we've evaluated these images, let's see some results and correlating scores. On average, our generated imagery got a higher FVIPS score than the baseline for all three experiments, including the physics uninformed model that we started with, the slosh physics informed model, and the high resolution physics informed model. We constrained generative vision models with physics-based inputs to visualize future flooding, which is what you see in the bottom row of images here. In other words, we set out to help city planners communicate more effectively, more visually, and more intuitively about flood risks in order to support climate resilient infrastructure development. And we have done that. Going forward, we'd love to see other researchers build upon this work. We intentionally made our system architectural generalizable. We applied GANs to earth science, and we look forward to applying this method to visualize the impact of climate extremes on different geographies, different times, and different disasters. We'd also love to see our work integrated into existing systems and making it publicly available. We could not have done this without the incredible support that we got from both our mentors and our partners inside and outside of FDL. I learned at 10 years old how humbling nature could be. And climate change will only intensify these natural forces. But together, we can build technology that supports a world in which all of humanity is resilient to climate change. Thank you.
Great. Thank you so much, Earth Intelligence Engine team. So I'm going to invite the whole team as well as our panelists back. So for this one, I loved you guys' slider, by the way. I would like to ask the panelists if you guys can share in one sentence what you would like the Earth Intelligence Engine team to work on next. So to kick us off, Rodney.
Well, that was a stellar presentation. One of the things that immediately comes to mind is transferability. How well can using this approach be used in a completely different set of circumstances, and to some extent scalability? I think it's really useful to do a proof of concept. And I really believe, trying to determine how best to deploy this in operational setting is extremely important, as well as scalability and transferability.
Great, thank you so much, Rodney. And Scott.
A U.S. Association of Insurers believes there's a $20 billion market for flood insurance up for grabs. And what you've shown here is the blend of AI models with physical models that's doing things better than either apart. So I highly encourage you to look at that market, because there's a lot of people who'd love to see this.
Great, thanks, Scott. And then Aaron.
Yeah, I would really, I'd love to see the work here applied to future climate projections. It'd be invaluable knowledge to all out there.
I absolutely agree. And I hope you guys continue on with your work. So I'd like to thank our panelists and our team. And to kind of continue talking about floods, I'd like to play a video from our partner, Google.